Okay, thank you. So good morning. It's really my honor to be here. I talk about the AI many times, like to various group of people with different focus. So this morning I'll try to share with you my point of view, because many people when I talk customer when I talk to them, many of them reflect that okay, like, yeah, AI has been a while for more than perhaps 40, 50 years. So it's going through what we call a period of enthusiasm and also a period of winter. So with this, like for the last 2-3 years, we talk a lot about the AI. So with this kinds of enthusiasms be continued. So I'm trying to look at that from two perspectives. First of all, in order to achieve that, there got to be some sort of next wave of business innovation, and there got to be a next wave of technologies innovation. So I'm going to look at that from these two perspectives and share with you my view. Okay. So again, yeah, this is the questions. Okay. Can AI do anything for business? Early this morning, Sunny talked about this AI. AI is basically not just for the large company, it's also for SME. In fact, when I joined this IT industry more than like 30 years ago, so I visit my major clients, so they all have this MIS department or data processing department. So every big organization, they have the data processing department. EDP, data processing, is a way for them like to get this competitive advantage. And then at the end of almost like late 80s, so when I visit other customers, small, medium customer, I also find that they have this small IT department. Even though they don't have this IT department, they do have a number of people doing IT. So I see today, this is also happening again. When I visit a major customer, I've seen they have established the big AI department, like they're hiring data scientists. Sooner or later, I'll see, okay, even SME, they're going to have this people working on AI. I'm going to see like AI will be really integrated into every business process or even into every aspect of our daily life. So this is my perspective, okay? And if you look at some of this research figure, so for all those staff, like last year, they got this first round of financial support. The number of this staff working on AI has been increased dramatically when you look at this, their company, the URL, the domain, right, .ai. So you find that there are numbers of new companies, or start companies, working on AI project. What does that mean? That means we're going to see many more AI applications available, okay, for us to use. And also, like in this region, like China, they would like to play a very dominant role in AI. So that's why I'm going to see there will be lots of talents, lots of new idea application available in this part of the world. Okay? So there are a number of success. In the past couple of years, there are a number of success in AI. I talk about this winter, AI winter. There are many reasons behind. Perhaps due to the availability of the data. If you would like to build models, so you've got to have a sufficient amount of data. Perhaps due to the amount of data, we really cannot make AI flies. Or perhaps due to the computing power available. Even though you have the data, whether we have this computing power to process those tremendous amount of data. Or perhaps due to the limitation of this AI algorithm. So there are various reasons behind. But for the past couple years, we have already like got through some of the hurdle, and particularly we do have a lots of advancement in some of the area related to like language translation, speech recognitions, language understanding, object detections, facial detection. So we do have lots of advancement in those areas. And earlier you have heard the previous presenter to talk about like applying these two technologies in the context of smart city, for example, right? So, but I still see there are lots of opportunities being untapped, okay? With the convergence of this AI, the big data cloud, I see there are lots of opportunities available, right? So this is just a very simple example, like this is a gaming company actually, so they build a little game with little IoT devices, install on toothbrush, okay? Educate the children how to brush the teeth properly, right? Okay, so they learn from that, okay, the AI model, this is the best way to brush your teeth. Perhaps the parent also got information and read the children out, they skip like the brushing for 2 days, right? So they have all sorts of information leveraging the cloud, the big data, the AI, right? So I see opportunities, business opportunities like that, application like that, okay, will be appear more and more, okay? And so as I said, I'll see AI will be integrated tightly with our daily living. So our view is that like the AI, the machine intelligence is not going to replace human being. It's much more like a collaboration. It's not man versus machine, it's more man and machines together. So in order to make man and machines together, there are a number of hurdles we have to address. So we human beings would like to have some sort of interaction, would like to talk to human rather than talking to a machines, right? So there's something we need to do in order to get this AI to be integrated into our daily life, okay, into our business. So the first thing, like perhaps you've heard about the soul machine. So today, soul machines basically like this is what we call the digital human, the digital concierge or virtual assistant, whatever you would like to call, or avatar, right? So today we're not just training this virtual assistant, the chatbot, or in the market they call chatbot, right? So we're not just training the virtual assistant with a specific domain knowledge, but we also train that with the emotions. Like when this virtual assistant, right? So talk to for example, this is a customer service rep. So when you talk to the customer, they also observe like how the customer talk, their facial expression. We said a face expresses 1,000 words. So the digital assistant, by looking at the response of the customer, perhaps they know the emotion, right? So they should adjust the tone, right? How to talk to them. And even we make it much more advanced. This digital assistant, even though like when this digital human responds to the customer, right? It's not just playing the sound, but actually saying the words. So for those people with this hearing impaired, actually those people, they can read the lips, okay, to understand actually what this digital assistant said. So this is what I would like to say. So we should go a step further. This is what I call the next wave of business innovation. Okay, so it's being used in Air New Zealand, okay, as people to help this passenger answering questions. In fact, it's very interesting that digital assistant doesn't even have some sort of personality and also carry some sort of accent, the Kiwi accents, right? So to make it more human-like. So the other things that area that we are looking at is the debating technologies. The debater, right? So we sort of like leveraging AI, okay, try to come up with some argument, okay, because we know that there can more than one answer or to a questions or scenario. So what we need to do is perhaps AI can help us to construct some argument. That's really useful. For example, I'm from the sales organization. When we want to negotiate with our client, how to construct some persuasive argument, okay, the pros and cons, right? Or even the government, they're looking for the policy, they may want to have this AI to come up with different perspectives. So this is another area, the debating technologies. And perhaps let me just go, and then the whistle. The whistle, we are coming to a stage that we can beat the human parity. We can even do better than human in the whistle recognition area. So this is very easy. We can identify using this AI. We can easily identify this is a strawberry. But what's more, we can go into a bit more fine granularity. Perhaps we know this is a strawberry dipped in chocolate, right? So perhaps we can also know the context, right? So this is what we are heading to, right? And if I look back to this, so this is what I call the multimodal AI. So this is a video clips, okay, playing this tennis tournament. So we're not just transcribing the voice, the commentator's voice. Perhaps we can also find out what's the most exciting moment by looking at what? the facial expression of this player, or perhaps those who are watching the game, okay, the audience behind, or perhaps we can also hear, okay, whether they're cheering, the voice of the commentator, right? Is he very excited when he's talking? The gesture, okay, the fist, like fist pump, high five. So when we look at this video, we're not just telling our audience, okay, there's a players, okay, there's a tennis player, but we also try to follow. This is a pretty exciting moment, right? So this is what we're doing. So you see there are lots of opportunities behind by doing that. And this is a little things that I did a couple months ago. So I tried to play around with that. This is a multimodal AI, doing visual analytics, doing voice detection, speech recognition, right? So I just upload video clips from Perl, okay? Just 30-second video clips, okay? So I try to build something, and then I can do this transcription, okay? The video transcription, what they said, and also the scene, okay? Okay, what's in there, okay? The concept behind. So as I said, the image, the video, the recognition, we are almost like surpass a human being, okay? We can not just understand that this is a strawberry, this is fruit, but this is a strawberry dipped into the chocolate. This is not a dog, this is a certain species of dog. So we can do that like even better than human being. But in terms of the speech recognition, there's still a challenges, okay? So this is what the industry would like to do to benchmark how good they're doing in the speech recognition. So basically, we use two types of corpus of the data set. First of all, we call it the switchboard corpus. So basically, it is the dialogue between two persons talking about this daily business. So it's much more business conversation. And then we have another kinds of data set, right? So it's more like we call home corpus. It's more kinds of colloquial talking, like talking between family in different topic. Okay. So we're trying to see how good we are. The speech recognition software, how good they are in terms of handling corpus like business conversation, or we really understand the content, or this is what we call the home corpus, like more colloquial. So this is what we are achieving today. This is from last year. I'm not trying to say IBM is better than the other companies, just to give you some figure. So like the human being, we still mix some error. Like we lost like one or two words in a 30-second conversation, but that's okay. Like the human being, so the human parity, human error is 5.1, and we can achieve like as of last year for this switchboard types of corpus, the business conversations. So we can achieve up to around like 5.5%. So pretty good. We still have to do a lot in this core home corpus, so around 10.3%, whereas human beings around like 6.8% error. So when we get through that, I'll see there's another kinds of business innovations coming up. And other interesting is that like lots of people, they focus on speech recognition, speech to text, but equally important is the text to speech, the synthetic voice. I talk about we would like to talk to someone that's more human-like, right? So the synthetic voice is also very important. So we can give also when I hear a Sunny, he carries certain kinds of persona, right? The way he talks, okay? The pace, the pitch, right? Perhaps Peter, like so this is also very important. So that's why this is also one of the areas, especially in the gaming industry. Like if you mouse over this game, different character, you would like to have different kinds of voice. When you hear the voice, okay, so you sort of understand the personality. So this is also something that we're doing. Like you can play around that, create a profile for certain character, the pitch, okay, the formations, the mood, okay, the effect. So you can create this person has this kinds of speech profile, okay, the sound profile. Okay. So the other aspect, as I said, is technology innovation. So are we okay? Some company they start to see the benefits of AI, but would that stop there? Would it be stopped just there due to limitation, perhaps the computing power? So this is something that we would like to address. Can we do something? We see everything has a limitation, but can we push that to the limit, or can we have another way of doing that? So this is something I would like to talk about. The AI, when you look at the AI, the foundation of AI basically are three things. You've got to have tremendous amount of data, right? So to train the model. You've got to have a very good algorithm, multi-layer deep learning model, right? But then very important, you also need to have the computing power. So we heard about this Moore's law. We're going to the end of the life of Moore's law. Can we extend that? So this is something that we are going to do, or we have to do. So even though you have tremendous amount of data, you have billions of algorithms, or the algorithm is improving, you still need to have a very good computing power, the computing architecture, or the way to compute those information. So if you look at the very simplified version of the deep learning algorithm, basically I want to build a model, try to train a model, right? Try to detect an object, whether this is a cat, a dog, a fox, or something. So I have this very simple deep learning algorithm, multi-layer, and then try to find out whether this is a dog and cat. So basically, when you look at this deep learning algorithm, there's two major steps, okay, that require computing power significantly. First of all is the forward, what we call the forward propagation. Basically, it's a bunch of the matrix multiplications, and then we have this activation function, right? The neuron. So this is non-linear functions. Okay. So this is the training, and then we have this what we call the backpop. So you got this, you label that, but then there might be error. So you need to adjust the error. Okay. So there's a backpop basically to adjust the weighting between those neurons, like those lines. So basically, there are two major areas requiring computing, and then we all understand that GPU is really good at doing this matrix multiplication. Perhaps like with the GPU, we can build a very deep learning model. But what if we have like tremendous number of data? Like the GPU has a limited memory, so that sooner or later there will be another limitation coming up. So this is basically the depiction of the previous slide. So we have this multiplication, we have this activation functions, we have this update, the backpop, right? So basically this is a mathematical operation. So what we would like to achieve is that, so if we would like to drive this AI, so we've got to have a new data algorithm, but do we have sufficient power to do that? So this is what we would like to see. We would like to see at least to have like 2.5 times of performance years by years in order to keep the momentum going. Okay, this innovation in AI. So here is where we are. So how to keep this 2.5 times performance gain? Performance gain in terms of a number of floating point calculation, the gigaflops per watt. Okay, we would like to see that 2.5 times. So otherwise, we see there will be limitations, so there will be some sort of like hurdles for this development of AI in the industry. So the things we did is, first of all, we're thinking, can we push this Moore's law further? So 2 years ago, we announced this 10 nanometer computer chips, and just last year, we announced this 5 nanometer computer chips. So we work together with Samson. So which means that we can have a more denser circuit, so we can deliver better performance with equal amount of power being used. So this is something that we are doing. First of all, like, can we push the Moore's law, extend the life of Moore's law? So the other things that we're doing is from the device accelerator perspective. So to keep this 2.5 times, so we're thinking perhaps in the AI area, maybe we can do something just like this. So this is the Mona Lisa, right? So the number of pixels being dropped, but we still sort of recognize this is Mona Lisa. So can we do something in the AI arena if we use less precision machines, right? So use less power, simplify the circuit. Can we achieve the similar result? So this is what we call the approximate computing. So we're trying to use this, what we call this reduced or mixed precision accelerator. So you look at this step, right? The calculation, the matrix multiplication, the sigmoid function, blah, blah, all this. So perhaps in some of the steps, we can use a less precision kinds of calculation instead of use a double precision. Maybe we can use a single precision or even half precision. See if we can get a similar result in the training model with similar laws. So this is something we're doing, and we believe it's something we can do. And also, perhaps we can also use some sort of distributed architecture. I mentioned to you the GPU is great, but then perhaps if we need to train large amount of data, terabytes of data, so that will be limitation in the memory alone. So what we're thinking is, can we distribute that? So this is something that we're doing. So maybe we can distribute that into multiple systems, leveraging parallel CPU, GPU, right? So to achieve something. So this is a benchmark we did earlier, and we announced that compared with another same benchmark that Google has been doing. Google did last year using the TensorFlow. So this is basically a logistic regression looking at around like 4 billion of record. Those are advertising, the clickstream record to determine whether certain people will click on this particular banner. Okay, so we build a training model on that. So we're trying to see, can we have a better architecture to push the limit? So Google actually was doing great, like 70 minutes they can build a training model, looking at like terabytes of data, 4 billion row. But with a better architecture, we can bring that down to 1.5 minutes, less than 2 minutes. So this is something what we would like to see that will be happen. So AI winter due to computing power limitation, we thought we might be able to get over that with different kinds of ways of doing things. And then there's also like what we call the phase change memory. So we understand that moving data from memory to CPU requires some sort of overhead. This is the traditional one-Newman architecture. So we have the memory, we have the CPU and I/O. So we're thinking, can we have the processing power within the memory? Okay? The memory can store information at the same time, can also process the information. So this is what we're trying to do. By doing that, we can perhaps achieve the graph that I just showed you. And this is something that we're doing. We're building a million phase change memory devices, running unsupervised learning algorithm, looking at this temporal data. Actually, those are the climate data, and then we're able to find out the correlations. Okay, and we achieve like 200 times gain, like in terms of the gigawatt per watt. Okay, and then finally, we understand that today, even the largest computer in the world can still not be able to solve the problems, related to perhaps related to the material science. So this is something that we believe may be able to help. This is a quantum computing, and the intersection with AI. We see AI will be a driving force to push quantum, like more people, researchers, the vendors, they spend more investment in this quantum computing area. We expect that will be something for the future. And this is very simple representation what quantum computing is. So traditionally, we understand that information can be stored as a bit, in the classical computer. So the bit can be 0 or 1 on your left, But then in the quantum, we call it the quantum bit. The information is stored in quantum bit or qubit. So it can store 0 or 1 or both. So this is the interesting part. So in the quantum physics, we call it the superposition. So with this kinds of characteristics, that can be a very, very major breakthrough. So this is just an example. I try to illustrate the idea behind. Say, for example, this is a playing card with 3 kings and also 1 queen. So so what we like to do is that let's flip the card. And what we need to do is find out the queen. So we have 4 cards. The queen can be happen here, right? Here, the queen can be happen here. So that can be, if we say, if this is a queen, we label that this is a 1, right? So king, queen, so 0, 0, 1, 0. Or queen can be here, right? King can be here, so that will be 1, 0, 0, 0. So if we would like to write a program to solve that, first of all, we need to load this into the memory, right? So we need to store it in the memory. So perhaps in this case, it's 0, 0, 1, 0. We store that in the memory, so we write a little program, and then we try to find out where is the queen? Which card is the queen, right? So obviously very easy. So at least randomly, if we randomly pick 1 to start with, on average, you find the queen, you need to have 2 flip or 2.5 flips, right? But if you're using the quantum computer 2 qubit, we can find where the queen is in a single shot. So this is the beauty of that. So just give you an idea. So So dramatically, it's not like we're giving them more CPU power, running faster. It's dramatically different in the way processing the data. So we see there will be some major changes. And then this, as I said, perhaps today there's some problem, easy problem that can be handled by a traditional classical computer, but there are also some soft problems related to chemistry, related to optimization, related to machine learning. It might not be able to handle easily by the classical computer, and the quantum computer is something that we would like to go for. And then today we have already have 20 qubit computers available. 22 bits mean 2 to the power 20, right? And then we also have 50 qubits available as a prototype. So we see when we have a quantum computer passing the range of 50 qubits, perhaps 60, 70, 80, that will be a very, very dramatic changes in the whole world. So let's wait and see. I guess it's almost time's up, so I'd like to stop here and then we can talk more during these interactive sections, and I hope you enjoy the section.